The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Like to do today is continue a bit with a survey of third-order spectroscopies. Little bit faster, little fewer equations, just to give you a feeling for what we do with them. So third order, just from last time, remember, if you do a nonlinear spectroscopy or you're not sure but you think you do, chances are you're doing a third order nonlinear experiment. So it, also known as four-wave mixing. It's basically all of the coherent ultrafast spectroscopies. 90% of them fall into this class. So we're talking about things like photon echoes, transient gratings. All of the standard pump probe or transient absorption experiments, whether you do that with coherent detection or incoherent. Basically 90% of all of the two-dimensional spectroscopies that are being used these days. Can't write and talk at the same time. And there's a few other examples. So I want to go through some of these just to kind of give you a feeling for how they're all held together and they're all related to one another through these third-order nonlinear response function. Yeah.
Does anyone do second-order stuff on non-centrosymmetric materials?
So that, well, the classic example is surface selective experiments, where you're making use of the surface to break the symmetry and look for surface selective things. But it is true. You could absolutely do nonlinear stuff at second order in a non-centrosymmetric medium. But just because that's relatively rare and also bloody hard to do, most people don't do it. Okay, so last time we talked a bit about photon echoes, but sort of what I'm hoping, and the other big class are coherent Raman spectroscopies. And that refers to many different sorts of things. Okay, so I'd like to keep going through this list a little bit and try and tie them all together. We talked about photon echoes and the ability there to talk about heterogeneity in a sample using the rephasing characteristics of some of the correlation functions that contribute to the third order response. Let's pick it up now with transient gratings. Transient gratings that are great experiments because they have a very nice physical picture that goes along with them. So just to review for a second, we're talking about degenerate four-wave mixing at the moment. All the colors are the same. It's very commonly performed in this box geometry. We generate a signal in the fourth corner of a box that dictates a particular phase matching condition, and we then can control the timing to sort of select different contributions. Okay. So the transient grating refers to the specific case where the first two fields are time coincident and they act as a pulse pair that is a pump field, and there's a time delayed probe field. Okay? So what we're talking about is we're going to generate a signal in one corner of the box, and any adjacent pair of these beams are going to be timed up with one another. We'll call them 1 and 2, but in practice, because they're time coincident, you can't distinguish which is first and which is second. We'll just call those, I guess we could call them pump. And then there's a probe. And if you now work through all of the processes that will contribute to this, well, the first thing you realize is the time variable that you have control over is after the second interaction with the light and of the light with the matter. And so in your response functions, you're looking at the T2 variable. And that has many contributions. We'll talk about those. But what you're doing is looking at relaxation of whatever happens upon excitation with that pulse pair. Okay, so the nice thing about transient gratings is that you should recognize that when you have two fields where the wave fronts, are perpendicular to the direction of propagation, and you cross these simultaneously in a sample, that one has constructive and destructive interference in the crossing area. And you can think about this by sort of writing out the product of those fields, and it'll look sort of like a magnitude and something like cosine omega 1 minus omega 2 t minus k k1 minus k2r. Hope I got that right. Let me see. But in any case, what you have is, let me just write it, just to make sure I don't screw anything up. expi. What you have is you have a spatial variation of the intensity and phase pattern in the sample over here. Okay, that's encoded over here. So K1 minus K2, the difference in the wave vectors for the two incident pumps lies perpendicular to this direction which you're propagating the beams, and it's an interference pattern, which, if you think about it as intensity, would be sort of a light, dark pattern. But at the same time, it's also a phase variation at the field level. And this is the pattern that gets imaged into your sample through the light-matter interaction. So if we're talking just about exciting population, we're saying that we're going to create a spatial variation of populations that are excited. And so by imaging that optical pattern into the sample, what you've done is created a grating. Right? It's a spatial variation of the complex index of refraction. So they're both the absorptive and the dispersive parts. Okay. The nice thing you have is you have control over the grating wave vector, because that's really just dictated by the crossing angle. So as I've pointed out here, if you cross by an angle 2 theta, then the grating fringe spacing is dictated by the wavelength of the light and the sine of the crossing angles I've written up there. Okay. So this turns out to be very effective, particularly if you're interested in watching relaxation processes on spatial scales, of optical, the optical wavelength range. Okay. So, yeah.
Does anyone know how to do microscopy on that? Like image that?
Yep. I think a great example is what Andy Marcus does at Oregon. He's really trying to look at anisotropic diffusion, perpendicular and parallel to fringes in an optical grating. Yeah. It's sort of the transient gratings are pretty much analogous to pump probe experiments. They are sort of the limit that the crossing angle goes to 0. And the fixed experiments that Andy does are functionally the transient grating version of what fix is to fluorescence correlation spectroscopy what transient gratings are to pump probe experiments, if that makes sense. It's the same kind of technique, but you're making use of this spatial variation to tell you about anisotropic behavior. Oh, okay, so, but now as you can imagine, there's all sorts of ways in which this grating can relax. You know, what I failed to point out is, okay, you've imaged a grating into the sample, and now what you can think of is that the probe pulse is something that diffracts off of that grating, that the efficiency of light scattered off of that grating is what you were measuring in a transient grating experiment. So that, that's sort of the physical picture that goes with it, and you can imagine a bunch of different types of relaxation processes. If you're just looking at relaxation of excited states, this is the amplitude of that grating gradually washing out with time. And you know, you can imagine that that would lead to a signal where the scattering efficiency just decreases with the relaxation processes. It's also possible that if this grating is imaged rapidly, that you can jump the index in, you know, functionally heating or expanding the material in the high intensity regions, and you can launch acoustic waves that propagate, counterpropagate actually through the sample. And as you might imagine, that will modulate the diffraction efficiency as they move across. And so that would typically, you know, show up as modulation on, you know, on top of a relaxation process. Time scale, of course, there is dictated by, you know, acoustic propagation. So you're, you know, soft media, you're talking sort of nanosecond behavior usually. And then, as you might imagine, you can look at very long thermal relaxation processes. If you're really heating the system in these light spots, then you've created a modulation in the index of refraction because of the temperature dependence to that index. And as that grating starts well-defined and gradually washes out due to thermal diffusion from peaks into nulls, that also contributes. And so basically, at the end of the day, any sort of transport process that has a wavelength dependence to it or a intensity dependence to it, that can be, and that'll work on this distance scale of the optical wavelength. You can probe that with transient gratings. Okay, any questions on that one?
So, do you ever do experiments where either the pump or probe in a transient grating is actually not so transient as a CW beam? So you either have like a optical grating there and you image it with some transient probe, or
of actually imaging the grating itself. I don't know. I think we're going to ask that to the Nelson folks. I think you guys were doing something like that in that. But
it's not a CW.
No, but not CW, right? Yeah. No, but this is getting back a little bit to what Paul was asking earlier. There are some microscopies in which you can really image the grating directly and try and use it to distinguish diffusion of particles, you know, along the direction of the fringe, the grating wave vector. But no, I mean, the way you described it, that's very uncommon. Yeah. But it's true. You can just as well do this with CW beams, but at that moment you also want to recognize that there you can't enforce the kind of time ordering that we have here. There's in addition to what I've described, there will be additional relaxation processes that, you know, depend on you know, coherence that different. Here I've described it really all as incoherent relaxation processes, right? Now that's not that's not entirely the case, and this is sort of getting toward coherent Raman methods. The other way to look at this is just because the wave vector matching and the time ordering says that there's a difference in wave vector between the difference in momentum between the first two interactions. That also means that there's a difference in frequency. So for degenerate cases, you know, this disappears. If these are slightly different frequencies, you have You can now imagine this experiment as a Raman experiment, where you're driving coherences at the difference frequency between the two incident fields. That creates a moving grating, right? It now moves in time and in space, right? Yeah, so we'll get to coherent Raman a little bit, but the grating can be...
Just one other question, too?
Yep.
So, what if you make your grading out of more than two beams? In particular, if you want to make not a 1D grading, but a...
Sure.
Is that something like it's actually possible to do?
Boy, yes. I mean, there was a time where people really talked a lot about holographic data storage, you know, with many beams. Right, and I don't know a heck of a lot about that, but that, of course, that would fall into a you know, sort of another class of light matter interactions. There you're going to need additional fields, but it's right. That's analogous.
Okay. It seemed like those things never actually got experimentally realized.
Yep.
Experimentally, is this really hard?
No. Nope.
Okay.
No problem at all. Yep. Okay, so now let me turn to transient absorption. I wanted to save this a little bit just to put a slightly different spin on it. What we're talking about now is really any sort of an experiment where you're using two fields, driving the system, waiting a period of time, and then just watching the response. So this is probably the most common type of an experiment. And I'm going to specifically talk about the case where, you know, I just cross two beams. I've got one that precedes the other. I call the first the pump, and the second the probe. There's one time delay between these two. And what I'm going to do is put a detector on the transmitted probe beam, and I'm just interested in looking at the change in intensity that I see with and without the pump beam there. Okay. So this is transient absorption, and what I'm talking about applies pretty much also to the other common case, which is that you're looking at spontaneous emission or some sort of an incoherent process from the sample, and you're looking at the change of that scattered intensity as a result of these two interactions. Okay. As we talked about last time, the formulation for this is a little bit different. You got to tweak it a bit, but it follows the ideas we're going to talk about. So what we are talking about here is any experiment in which you've got three independent variables. Okay. Up here, I just want to point out, remember in our third order response function, this involves three independent time variables. The time delays between different fields, those are the ones we like, or three independent input frequencies, or some combination thereof. Okay. And in the case of pump probe experiments, the way we think of this is that this is the three variables that we have control over are, you know, the frequency of the pump, the frequency of the probe, and probably the time delay between the two. Okay. So that's the first clue that you've got a third order experiment. Okay. And so, yeah. Well, okay, so the first thing to recognize is that this two-beam experiment and the change in intensity on that signal detector really can just be thought of as a coherent third-order experiment. If we go back to you know, a standard box geometry here, and we remember we thought of the transient grating as being this pump pair spatially separated and crossed in the sample, and then a probe. If you take the limit that pulse 1 and 2 overlap, and that they in fact come from the same field, that's just a pump probe experiment. That also means that as you're gradually approaching collinearity here, it means that the signal is gradually becoming collinear with the transmitted probe. And so what you're really observing when you look at the intensity of the transmitted probe is a sum of two fields, the transmitted field and the generated signal. Okay? And so that's sort of the coherent description of a pump probe experiment. And so then, you can start talking about, okay, what is the change of intensity that I see when I add the pump beam as a function of this delay? And it is basically going to involve, what is the intensity with the pump there minus the intensity without the pump there. Okay. So you had a question?
I just want to clarify some language in my mind. What you just described, is this the same as saying that the pump probe is always heterodyne? Like just
Yes.
itself?
Exactly. It's intrinsically heterodyne. That's the word we used for it. Yeah. So that's sort of what I want to show here, is that it is, you're not actually measuring a technique, you're not measuring an intensity actually, but you're really measuring something directly proportional to the polarization in the response. Okay, so if you think about this a little bit, the intensity with the pump there is going to look something like the intensity of the transmitted pump light and I'm sorry, the field of the pump plus the signal, and of course the intensity is going to go as the modulus squared. And then you're going to subtract away just the intensity of the probe beam itself without the pump. So this is, oh, I'm sorry, I'm getting this wrong. Intensity of the probe beam transmitted. Subtract that away. Okay, so technically this is what you're measuring. Okay. And so you're typically working in a regime where this change of intensity is small compared to the intensity of the pump probe itself. And so what you're saying by that is that the magnitude of the probe, the field, is going to be much greater than that of the signal. Okay, oops, I'm confusing things here. And so based on that, we can expand this out. You can see what happens is sort of the biggest term, the leading term, which is the intensity of the probe, here and here, those subtract away. The square signal term, we're going to ignore that just because it's small compared to the cross term. And the cross term, looks like okay, and so this is just the real part. By the way, I've left out all the proportionality factors here. This is just the real part of the probe times the signal. Okay. And now, if you look at which of those quantities are dependent on this time delay over here, well, this is just a constant, and so you really have something linearly proportional. This is the function of the time delay. You really have that the change in intensity is linearly proportional to the nonlinear signal. Okay, and just remembering that the signal had a pi/2 phase shift relative to the nonlinear polarization, and also remembering that for our purposes that the nonlinear polarization is proportional to the response function. What we are really measuring is the imaginary part of the product of the probe and signal probe field and signal polarization or nonlinear response. Okay. Which is sort of what we expected, right? You would think of this experiment as transient absorption. How is the absorption of the sample modulated by the pump beam, right? And that's just what we're looking at here. The imaginary part of the polarization is the absorptive part. Okay, so it's just like you said, that you can think of this as the transmitted field being a heterodyne, a phase-locked heterodyne field that's that you're beating against the system. And that, for an incoherent experiment, you're going through an awful lot of math to describe that, but it makes a lot of sense when you start to look at wave packet dynamics on pump probe experiments. Okay, any questions on that? Okay, so just let's see. So as you might imagine, let me just go, just for purposes of making this easy, let's see. As you might imagine, any sort of relaxation process that contributes to the absorptive, the imaginary part of the polarization, the absorption change in the sample, as a function of that time delay, you're going to see it. And now, one other thing to point out is, when you write out all of the possible dipole interaction processes that can contribute in that signal direction, it's all 4 of the possible correlation functions in that nonlinear response. And so what you will see is a number of different contributions. Probably the one that contributes to everyone that does this experiment is that delta I will look at the population relaxation in the ground and the excited states that you are coupling together. So if you imagine you do these all with this, the same color experiment, now what you're doing is, call this one A and this one B. You will find that there are processes that tell you about how fast does population relax out of the excited state, and furthermore, how does population return to the ground state. You can think of that as the pump field not only creates an excited state population, but it also creates a bleach, a hole in the ground state. And you watch both of those things. In the limit that you return from the excited state to the ground state, this becomes a simple exponential, but could be more complicated than that. Okay.
It's coupling through the fat states.
Well, you can imagine, yeah, right, if you mean by dark states here, right. So you can imagine, say you have an intermediate state that you relax through on your way down, then the rate of leaving this state and the rate of arriving here is going to be different. So seeing bi-exponential behavior shouldn't be a surprise, right? Okay, so now this way of thinking about it really applies to experiments that look at wave packet propagation, whether you're talking about electronic or vibrational spectroscopies. Basic idea is, it's pretty common that you see experiments that describe starting in some electronic state, propagating the system then on an excited electronic surface, and people probe this all over. If you really are interested in studying the system as a function of sort of the nuclear coordinates of the system, say in a reactive one, you might imagine choosing the probe, the pump and the probe frequency don't have to be the same at all, right? They are chosen to match certain energy gaps in the along this potential, and by tuning your probe beam, you can imagine pulling out the wave packet dynamics as a function of this coordinate q. Okay, so the pump and the probe are just independent variables, and you'll notice, going back to the wave vector matching, that that's the beauty of a pump probe in our language, is that it's always wave vector matched, just by definition how it's set up. Okay. So in the diagrammatic perturbation theory language, what we're talking about is these sorts of diagrams. So let me go back for a moment. I showed you that these are sort of the fundamental, 4 fundamental interaction processes for light coupling to a 2-level system. But in general, you can have up to 4 levels that are coupled in a 3rd order experiment. And this is just sort of generalizing those diagrams to 4 levels that I've arranged in a particular way, just because they correspond to this wave packet type of process. We have some processes that create wave packets in the, you can see here is a difference frequency. It creates a coherence, a wave packet in the ground electronic state. Whereas you've got others that create a wave packet on the excited state. Both of these then propagate freely during the second T2, the second time variable, one on the excited state, one on the ground state, and then you probe it. And of course, you know, you can choose where you probe it and how you probe it. Okay, so those are the processes that, you know, I was picturing here. That those sorts of diagrams are sort of the mathematical way of describing why one would see quantum beats, for instance, in a either a transient absorption or even an incoherent fluorescence experiment with two fields. By the way, one important thing I don't want you to carry away from this is that there is no simple connection between these types of diagrams that are really commonly drawn and the Feynman diagrams. These are not the same thing. It is true that there happens to be mapping onto the same energy axis if you're drawing ladder diagrams. But Feynman and ladder diagrams propagate the density matrix, and this is energies as a function of nuclear coordinate. Okay. So that what I'm implying by that is that when you draw one of these types of processes and say that you create a wave packet in a density matrix language, that is equivalent to creating a coherent superposition of two eigenstates of the electronic excited surface that then propagate. Okay. All right. Any questions on pump probes? Okay. Sort of in our list of things, what I'm hoping to do at some point is actually spend some real time on Raman spectroscopies, but just so that we see it, I want to talk a bit about Carr's spectroscopy, just as an example of coherent Raman techniques. So let me see. Now, I have to say, I think there's nothing quite as stunning as going into a lab that does Carr's in the visible, because this is one of these experiments now which is not a degenerate experiment, where you have multiple colors and you're specifically trying to take advantage of difference frequencies in the optical range to drive vibrational transitions. And you know, it is pretty stunning with people that do 3-color Carr's, where we really have 3 tunable colors incident on the sample crossing, and you get an enormous array of spots in every color you can imagine that comes out the back of the sample. And each one of these encodes some sort of a different coherent vibrational dynamics of the system. And Carr's is probably the one that has been around the longest and still is really important. So the idea here is, you can think of this as a Raman transition. And now this sort of emphasizes the fact that if you look at our nonlinear response functions, as long as, say, for instance, your first 2 fields are time coincident, you don't actually have to be resonant with a state during the time period between the first and second interaction. That just by the Fourier transform principle, if you remember those lovely sync functions from 5.74, that when time is very short, you can be resonant at any frequency you want. And resonance is only a condition that happens after several cycles of the field. And so this is the language for this is virtual states. And so what it means is if we take 2 fields and we are time coincident, we can generate excitations at difference frequencies. So we choose 2 fields, and in the Carr's language, this would be the pump beam and the Stokes beam. And what you do is then we'll call these, say, or what did I call them up here? G and E. The ground and excited vibrational state. And it goes through sort of a virtual state. And so this involves two transition dipole interactions. The first, so let's see, what do we do? Mu Vg, mu Eg, E V. Okay, they occur simultaneously, and now the system is in a coherence, and it propagates oscillating with time. This is tau 2, and we can say put some damping on this. This vibrational wave packet, this vibrational coherence propagates with time, and then we can probe it. Now, in practice, people use the same pump beam as also the probing field. Okay, and this leads to an anti-Stokes signal emission, which is at a completely unique color. So now, just looking at this process, this is omega pump. We can see that the signal is going to be plus omega pump for the first one, minus omega Stokes for the second one, plus omega pump for the third one. Okay, so that's 2 omega P minus omega S. So typically, you might imagine a green beam going in for the pump and a red one for the Stokes. And what you see is that you might have a green pump and a red Stokes, and you'll see sort of a blue spot out to the side. And you can understand that then immediately from this, because it also immediately says that the wave vector matching for the experiment is two momenta, units of momenta coming from the pump, minus 1 of the Stokes, and that leads to the wave vector matching condition that I've drawn up there, right? That we're going in the forward direction, and we bring in the Stokes at an angle. The signal field will come out at a particular direction dictated by the frequency and wave vector matching in one direction. Now, when you're doing this with well-defined frequencies, then the wave vector issues that we talked about yesterday come into play, and the angle between the pump and the Stokes become really critical to get efficient signal generation. Okay, but so you can see here, if you now do this with time-resolved pulses, that you can move the time delay between these pump and probe, and that just gives you the vibrational dynamics in the system. Right? And that is the time domain version of a Raman spectrum. Right? In the limit that you go to very short pulses with the same color, you should recognize that the transient grating experiments we did correspond to this process also, where this difference in colors, these are colors that both lie within the bandwidth of the excitation fields. Okay, so you can imagine that there's enough colors in your short pulses that they span this whole, the bandwidth spans this whole region. So they don't need to be different colors. Okay. All right. Yep.
When people do these cars experiments, do they bring in a local oscillator at some point to heterodyne the signal, or not usually?
So, yes and no. There's, in terms of people doing coherent Raman with heterodyne detection, I think there's not many people that are going a whole lot further than the Nelson group does, right? Although, with multiple colors. Now, that happens. There are a handful of coherent Raman experiments that do this, shall we say, unintentionally, and I think the femtosecond, the stimulated Raman spectroscopy that Rich Matthews does is an example of this, where it's sort of intrinsically heterodyned, sort of like the pump probe experiment. I'm actually hoping I can spend a whole chunk of time on coherent Raman, because there's a whole slug of interesting, techniques, and you do them with and without heterodyning, and lots of interesting information to get out of that. But the heterodyning idea has even been used. Heterodyning cars has also been used for imaging. That Sonny Shee's been doing some of that, although I'm not sure if he's real fond of doing that really tough experiment.
He's fond of tough experiments.
Yeah.
Another point is that most people do this in the frequency domain. In the frequency domain, it's important that you are okay. People usually have two green, like 2 megapumps the same beam, right? When in principle they don't have to be. So what's important if you do this in the frequency domain is that your last beam, your last megapump, is narrow band. Because if not, you're gonna wash out your frequency resolution is depending on your last beam. So you need to have a narrow band beam in the last beam.
Right. There's, yeah. Thanks for pointing that out. So what I described was sort of the time domain limit. Thinking about this as a time domain experiment in which you use a, short pair of pulses to create a vibration. You listen to it, and you're controlling that time variable. The other approach is, like Paul was saying, is treat it as a frequency domain experiment. You still, in principle, have this, control over this time delay, but it's very often that you might actually want to excite a range of transitions and look at the frequency-dependent changes and by spectrally dispersing, what comes out as a signal. And then Paul's right, is because the virtual state is at any frequency you want to use a combination of short excitation and narrow band probing to give you both the time and the frequency resolution. Okay, any questions? So I think now is a good time to take a break. All right, folks, what I'd like to do is sort of get into an introduction to two-dimensional spectroscopy, a little bit of motivating why you do it and sort of the general ideas behind it. I want to motivate it by a couple of the examples I gave at the beginning. Why you do nonlinear spectroscopy. It's if I have a linear experiment and I see two peaks, what do I use to interpret what the origin of those peaks are? I could imagine there are two entirely different molecules, spatially separated, don't know about each other, and they give rise to these peaks. I could also imagine that these arise from eigenstates that reflect the coupling between different electronic or vibrational states. How do you distinguish them? The other example, which is sort of analogous, is if you have a very broad line, do you think of that as that an inhomogeneous line or not? How would you go about tackling these problems? I think there's a real simple exercise that tells you that you should be able to solve these problems if you do probe experiments of the kind that we just discussed. What we talked about is that with probes, that we have 3 independent variables, and we tend to think of these, when we write out response functions, we have 3 independent time variables, but for pump probes, you can think of these as sort of being the frequency of the pump field, time delay between the pump and the probe, and then the frequency of the probe field. And now let's just actually sort of consider the case where this is really a frequency domain experiment, just a double resonance experiment in which we independently control the frequency of the pump and the probe. Okay. So this is sort of what I refer to as double resonance 2D spectroscopy. Yeah, by the way, these ideas have been around forever. The only things that are new these days is the ways of doing them and thinking about the nonlinear response in terms of a huge 2- or 3-dimensional surface. Okay, so let's do that and apply it to these two problems. Okay, so here's how we're going to do this. As before, cross 2 beams in a sample. Here's my detector on here and measure the change of intensity on there as a result of this field. And I'm going to start with the spectrum, and I measure that with my probe field, so I'll call this a negative probe. And now imagine that I tune my pump beam to be on resonance with this state. So what could happen? Well, actually, just to make it more interesting, let's put a third peak in. So one way of thinking what might happen, just take the extremely intense limit. There's a poor molecule that's sitting under that frequency that is just going to get obliterated. We're just going to destroy it. Photochemically, bang, it's gone. What happens? If you've sort of somehow removed that set of molecules, it means you've really removed the possibility of making absorption at any of those frequencies. So really any sort of other transition that originated from that same molecule will also be gone. Okay, so imagine we go through now and we add the pump and we see that, oh, this intensity drops, this one doesn't, this one does. It says, boy, you immediately know that there's a spectral correlation between that peak and this peak. And it's the same molecule you destroyed. So what we're talking about in a more gentle two-dimensional experiment is that we're looking at the same sorts of molecular couplings that transfer energy from one state to another. And that means that bleaching one transition will lead to bleaches in other couple transitions. So what this means is now your change of intensity as a function of the probe is going to be positive and positive here, no change in between. And now think of this as one slice through a two-dimensional surface. Right? Now repeat that experiment for all possible pump frequencies. And now make up a map of this delta I as a function of the pump and the probe frequency. So this is one slice vertically through here, and it happens to be on resonance with that peak. You map this all out, and you would expect to see a spectrum that looks out like this. This is sort of the diagonal frequency axis down here. So what does the spectrum report to you? It says these cross peaks, that is, changes in intensity at frequencies different than where you pumped. It's telling you about the correlation between spectral features. It tells you about microscopic interactions. This tells you this peak is not correlated with other ones, whereas this one is. Or you can take the other limit. The intensity of those peaks will tell you how strongly they interact. So that's one way of ironing it out. And I'll take the same approach and, yeah.
Just as a practical question, is there ever any utility in placing your omega pump where you don't have a peak in the omega probe spectrum? Or are you just wasting time by...
I'm just, so when it comes to practical stuff, then how you do it is going to be different. But, so I'm just saying this sort of from a conceptual point of view. It is true, if you know the linear experiment and you know the pump interaction, then you at least know in one dimension where to go scan. And it doesn't count for the other dimension. Because you can open up new transitions with the first interaction that you didn't know about. But it is true, absolutely. If you've got a sparse spectrum, then you have a limited set of areas to go measure. This is the whole reason why I think the large fraction of high-quality gas-based spectroscopy really falls into this class of it's two-dimensional spectroscopy. It's presented as slices through a surface.
And it's because they're not sparse, so it's very hard to imagine visualizing.
Right, so then we start getting into sort of the practical issues about why would you do an experiment one way or another. You can imagine mixed time, and you can imagine I've talked about this as a frequency domain experiment, and talk about time domain grouping, and there's practical issues there. Okay, so, but one thing that, is great about 2D is that there is a great power into visualizing all of the interactions in one surface. There's a lot to that. This gets back to the issue of a spectroscopy is only as good as it can distinguish different models. And it's, it may just be me being a visual learner, but when you sort of see the interactions in the system just mapped out in front of you, it really gives you a tremendous insight in what's going on. Okay, so let's apply the same example then to this inhomogeneous line shape. So now
These are both CW.
yeah, just think of them, well-defined frequencies. Narrow band. Okay. Now imagine, say we have an inhomogeneous line. Okay, we'll do the same thing. This is our probe beam. We're going to come in with a narrow band pump, and now what happens is we'll sort of bleach a hole into this line. Or we're looking specifically at the case of an inhomogeneous line shape. So now the change in intensity actually looks quite narrow along the probe. And this also is one slice through a two-dimensional surface. If we look along the diagonal axis, this is the slice we took, and it's really quite narrow. Now if you map out the whole surface, you imagine seeing something that looks diagonally elongated like this. Okay, I'm drawing just sort of contours of what you might expect to see. So what is this telling us? Well, clearly you can see that if I take a slice along this diagonal axis, I'm really just going to be mapping out the large, broad profile that I saw in the absorption spectrum. But this hole burning experiment is clearly doing some sort of a line narrowing. And in fact, if you look at it a little bit more carefully, you can convince yourself that the slice along this anti-diagonal, but that actually gives you the homogeneous line width. So the idea is, this is sort of the idea of a line shape, that a line shape, and analyzing a line shape can give you some sort of an information about how the ensembles meet up. And this is sort of much more than just doing, say, a photon echo experiment, which gives you an average measurement. You can imagine that this line shape is composed of slightly different environments that vary with frequency, and that would show up as subtle details of what this line shape looks like. So there's a lot in then analyzing those contours. So that's sort of the motivation for doing 2D spectroscopy. These sorts of problems. Okay, so for the moment, what I'd like to talk a little bit about is this case here, coupled systems, because that's one of the big reasons to do. Yeah, actually, there is one further example I didn't think about before, but you can also use this to tell you about reaction kinetics. And you can imagine that you can pump, if you have sort of a chemical equilibrium, that you can pump one and probe the other, and then the time rate of change of heats in that surface tell you about the kinetics. But once you think about all the ways that people use a pump probe experiment that have been done for decades, you can see that there's a mapping of the two-dimensional spectroscopy. Okay, anyway. So one of the big applications is to understand molecular couplings and interactions. Right? It's trying to boil down the essence of what's happening molecularly that gives rise to a particular spectrum, and perhaps even trying to do things like invert a structure from it. And so to start with that, I just wanted to, as I've said before, spectroscopy and modeling is all one and the same. We can't separate the two. And so, in terms of trying to describe what gives rise to cross peaks that reflect molecular interactions in the spectra, you really have to think about it in terms of a Hamiltonian that includes these sorts of couplings. So I just wanted to write down some of the popular ones, which you will see everywhere. And in one form or another, these are all the same thing with very subtle tweaks. For people that look at electronic couplings, in molecular systems, it's called a Frankel exciton Hamiltonian. Sometimes it's known as a coupled two-level system. For people doing vibrational work, you might talk about coupled oscillators. And all of, in essence, what you're trying to derive is the minimum Hamiltonian that describes the interaction between two molecular states. So these, at the simplest level, these can boil this down to a 2x2 Hamiltonian, two quantum states in a coupling. But so the basic idea behind all of these is that you imagine that I've got two different quantum states that may be on, and that I want to introduce an interaction between these two. Sort of coupling these two states together with an interaction B, we know that that sort of creates a common ground state and a splitting. Now the eigenstate, if this was, but this leads to a set of eigenstates. Let's see. In 5.74 we call them plus and minus, but I think I'll call them A and E. Let's see. Maybe I'll call this one A, B, C. And now these are eigenstates of the material Hamiltonian we've been writing down so far. And these now would be the states that one would think about creating resonances with in the Hamiltonian we've been describing, in the Feynman diagrams and the ladder diagrams we've been describing. So in any case, usually the information you want is back here. So all of this is constructed in this local or site molecular basis. So this Frankel exciton Hamiltonian, well, let me just start with something that will look familiar. Like a coupled oscillator, you imagine two vibrations. So something like square root over 2 M. Okay, there's one vibration, and there's another. There's two oscillators. Now you have to couple them together in some way, and that involves, in some way, a coordinate or the momenta of these two oscillators. So at the simplest level, you might imagine a linear coupling. So it's called V, or some more complicated combination of those things. This Frankel exciton Hamiltonian, it's usually written in terms of raising and lowering operators in the electronic states. Yeah, by the way, this is fiction. It might be energy of N. Two diagonal terms and a coupling. I just want you to realize that all that is shorthand for the 2x2 matrix that we know and love. Now so the thing I want you to see is that these are really functionally the same Hamiltonian, right? If you go now express your vibrational states of raising and lowering operators and just sort of take the leading harmonic term in these vibrations, H4, omega, M. term here is going to have all sorts of cross terms and interactions, right? Some of which will take the form I wrote up there. And extra stuff. So what are these things telling you? They're saying I've got two vibrations, two electronic states. There's a coupling, and that coupling will lead to, in talking in this molecular base, it's going to lead to energy being transferred from one state to another. In an eigenstate picture, translate this then diagonally. This creates a new set of split eigenstates. Okay, so there is a now for the purposes of 2D spectroscopy, we have to worry about a little bit extra. And that is, for electronic systems, we have to worry about the fact that there may be in the eigenstate picture, there's a common ground state, and then there are two singly excited states, also known as the one exciton states, and we can call those plus or minus, but for my purposes, I'd like to call them, use my vibrational language. No, that's not quite right. But basically, I have two possible states, and I can put one quantum of excitation into one state or the other. We have to recognize there's also the possibility when you start talking about multiple interactions that there's a 2 exciton state where you've got one excitation in each state. So in a coupled electronic system, there are really 4 levels you have to worry about. In a vibrational system, it's basically the same, except that with bosons, you can, unlike the fermions, you can put multiple excitations into the same vibration. So there's an additional process that when you think of the eigenstates of a coupled vibrational system, not only do you have the ground state, the singly excited eigenstates, but you also have 3 states, 2 quanta in either of the eigenstates, and also what we like to call the combination band. That is where you've got 1 quanta in each. And so it's these 4-level and 6-level systems that that are important to sort of understanding the origin of all the peaks in the 2D spectrum. So, okay, now when you go and apply the pump probe wave thinking, let's take this double resonance approach, and assume that the system always begins in this lowest lying state, then you can sort of immediately map out a set of interaction processes that will give rise to a set of peaks in the spectrum. So taking these two, so for the electronic case, you can see any initial interaction with the electronic system is going to drive one of these 1 quantum states. So you, along the pump axis, you know that you're only going to have resonances at, let's see, what shall I call these? A and B. No. Let's call this A, B, and C. Omega BA and Omega CA. We know that this is all of the peaks that we observe are going to have to be along these 2 directions. And that, in fact, you know exactly what your linear spectrum is going to look like then. 2 peaks that correspond to those eigenstates, the singly excited eigenstates. And now you look at the possible permutations of how the system can evolve upwards, and the possibilities involve, well, let me draw some possibilities. you'll find is that there's 6 possible processes. And actually, I'm offsetting these two, but the way I wrote the Hamiltonian, these are going to be sitting on top of one another. You'll see that these diagonal peaks and one of these cross peaks will all have a positive sign, and the other cross peak will have a negative sign. This is omega BA. Okay, what gives rise to these things? Well, first of all, the diagonal stuff, that should be obvious. This is just all the pump probe stuff we've already written before. That's a single transition where you drive the system upward, create a population in that state, and then probe that state. Okay. These cross peaks, you know, to first order, that is the process I described up there, the cartoon version. It is driving population into one state and then probing the other state. Okay. Now, this what's important is this other negative diagram, and that's where these 2 exciton or 2 quantum states come in. Those have opposite signs. This is going back to our how many times do you act on the bra kind of process. And they involve processes in which you excite one vibration and then add in another quantum onto the other mode. So let's see, this means A to B means we're putting, let's start in the ground state, put one quantum into state B, and then I'm going to add a quantum into state A. And then I'll probe that state. Okay. So now technically this transition comes out at a frequency, let's call this guy D. We started at omega BA, and then we're going to observe the system at omega DB. Actually, I'm really doing it wrong now. This negative peak is going to be at a slightly different frequency. Now, in this, one thing you'll notice is in this very commonly written Hamiltonian, in which you just have simple linear couplings, simple A dagger A terms, simple linear Q1, Q2 types of terms, and harmonic systems. Coincidentally, it happens, not coincidentally, quite on purpose, that omega BA and omega DC are identical. Not only that, but omega CA and omega DB, they're identical also. And what that means is you're going to have 2 terms with opposite sign that show up right on top of each other. It disappears. So for this kind of a simple system, and the same goes for a coupled harmonic oscillator system. Let's see, these cross peaks actually vanish. And this is a manifestation of the fact that there is no nonlinear response from a harmonic system. You need some sort of a more complex coupling and harmonicity in a vibrational system. That's the word we'll use there. Or this may mean other types of electron-electron interactions to give you a measurable type of coupling or interaction that one sees in a 2D spectrum. What do I mean by that? What I mean is, in a physical, just sort of from a physical picture sense, I need an effect where there is a difference where if I put one quantum of excitation into one state and then another quantum into the other state, that is not merely just the sum of the two energies. I need some physical effect where if I put energy into one state, they communicate with each other. And so by definition, I will need to put a little less or a little more energy into the system for that second quantum, just because of the initial interaction. And so how do you write those sorts of things? In the case of vibrational systems, it comes about from anharmonicities. It might be the higher order terms in the anharmonic potential. It may be nonlinear couplings. Over in the case of the exciton Hamiltonian, we're saying things like, imagine you have a coupling constant that goes as the ability to put an excitation into N depends on whether I have populated M. And the magnitude of that effect depends on beta. So you need a term that goes higher order than just simple AA dagger types of terms. What that leads to is a shift of this exciton state. Typically, anharmonicity in vibrational systems will shift down all of these levels. In the electronic case, you can imagine shifts both up and down, and it really just depends on the electron-electron interactions. If you have positive or negative coupling, positive and negative couplings can take this up or down, and that will dictate which way this peak shifts. And then what we do is go sort of analyze the splittings between these cross peaks, and that gives rise to sort of information about what the coupling is. These would be related to electron-electron coupling. Okay, so the vibrational system is exactly the same. I mean, at first level, you're going to end up with two diagonal peaks. These are now going to have a doublet shape, and that just reflects the fact that you have these two quantum states also, and cross peaks between them. And in this case, it's similar. That the way I've written that Hamiltonian over there, splitting between these peaks is, in the case that you have two degenerate oscillators, this is going to be twice the coupling. And that just reflects the fact that the energy of the combination band in a coupled system is typically written, it's omega 1, it's the sum of the two energies minus twice coupling between two states. You had a question.
So would that be the same whether you have intermode couplings or whether you just have diagonal anharmonicities?
So in this vibrational case, as it turns out, if you just do a simple linear coupling between anharmonic oscillators, you will get sort of anharmonically shifted.
What if you don't have couplings, so you just have two anharmonic tensions?
No, then you won't. Then you really have two independent oscillators. You need something. You need some sort of a term that allows the two to communicate. You do need something in one coordinate and the other. And what this is saying is that for simple harmonic systems or simple two-level systems with the linear couplings and harmonic behavior are sort of synonymous with one another. And if you have linear couplings and harmonic behavior, there is no nonlinear response when you really work through all of it. You will always find terms that have opposite sign that destructively interfere with other signals.
But if you had diagonal anharmonicities, it would get rid of that frequency matching between the two quanta levels and one
Yeah.
quanta. Yeah.
Exactly.
So would that get rid of the cancellation between the cross peaks?
Yeah, exactly. So you can take anharmonic oscillators with a linear coupling and it'll do just as you said. Okay.
Why are the peaks on the diagonal have two lobes again?
So that reflects the overtone. We put two quanta into the same vibration. So this peak reflects the fact that you can go 0, 0, 1, 0, 2, 0. You can pump the fundamental transition and probe the overtone transition. And that typically is anharmonically shifted by a little bit. If it's a harmonic oscillator, they're the same. And that's going to vanish. So again, for harmonic behavior, the nonlinear response vanishes. So another way of thinking about this, which might be more useful, is really just think of this as the sum of two very close peaks. And that you just are going to have net one peak whose amplitude is going to reflect the magnitude of the coupling. When you've got two overlapping peaks that are just moving a little bit, you can show that the amplitude of that sum is going to scale with the coupling.
In practice, can you usually resolve them as two separate pieces?
Certainly there's many times that we see it in the vibrational systems. But, if I kind of do a survey in my head of things I've seen, I'd say on average it's more like this, that you're looking at interference effects that it's hard to distinguish discrete resonances. But certainly in strongly coupled systems, there's many examples of this.
So doesn't that get complicated though, because your dipole moments will change to two constant state?
Right. So it is true. What I haven't talked about, you do have to worry about the selection rules. And so the way I've drawn this is using harmonic oscillator selection rules. And in that case, you're going to allow transitions between the ground and either of the first excited states, and then also between either of the first excited states and any of the upper lying states that are single quantum transitions, dipole, harmonic oscillator selection rules. So in this case, there's two. In this case, it's the same. You can connect the one excitation states to the overtone, but to the combination band, but the overtone states can only be connected to their initial oscillator. There are examples where you can start to pick out extra peaks that arise from the harmonically disallowed transitions. Okay, any questions on that? Okay, so I could get now into sort of the other example of looking at line shapes. I think it's better we just call it a day here.